Hello and welcome back to EGR 151 Electrical Machinery. In this unit, we're going to be talking about some basic trigonometry and about vectors. We will be reviewing these topics because they're going to be used in the next series of units on AC power. So what are we trying to accomplish in this unit? Well, we want to be able to define a right triangle, right? So understand what that is and tell what characteristics of it make it a right triangle. We're going to need to know how to use the Pythagorean theorem. In addition, we're going to be able to need how to use the Pythagorean theorem to solve problems, specifically with right triangles. And then we want to become familiar with the trig functions, sines, cosines, and tangents. So in terms of our AC or alternating current formulas, it turns out that many of these are going to be based on right triangles and right triangle relationships. This is due to the fact that the current and voltage are out of phase with each other, and they're normally out of phase with each other by just about 90 degrees. So many of the relationships that govern right triangles fit well with comparing voltage and current in AC circuits. Turns out that it's not exactly 90 degrees, and one of the things we want to find out about that is how much it is off by, and we're going to do that by a variety of different factors. So what makes something a right triangle? Well, it turns out that any triangle that has a 90-degree angle, also known as a right angle, is a right triangle. Another important term is the hypotenuse. Hypotenuse is the side opposite the right triangle. And it turns out that it is also the longest side. If you recall, the internal angles for a triangle add up to 180 degrees, so the 90-degree angle has to be the largest of the three, since the other two have to add up to the other 90 degrees. Another important individual that you should know about with right triangles is Pythagoras. He's a Greek mathematician that studied right triangles, and he discovered many of the relationships that we use today. And this was done several thousands of years ago, so the fact that this math has been around for a very long time. So here's our example of our right triangle. Right? If we take a look, right angle down here in the corner, right? Horizontal and vertical line. Opposite side is known as the hypotenuse. You're probably familiar with the relationship that Pythagoras developed. What his theorem states is that the sum of the squares of the sides of a right triangle is going to be equal to the square of the hypotenuse. It's actually shown here in this graphic. So in this case here, this is a 3, 4, 5 triangle. The 3-foot side, when squared, would be 9 feet. The 4-foot side, when squared, would be 16 feet. And the 5-foot side, when squared, would be 25 feet. And it turns out that 9 plus 16 equals 25. So Pythagorean's theorem works, and it works for all right triangles. Mathematically, it's shown that the square of the hypotenuse, c, is going to be equal to the square of the other two sides. So c squared is equal to a squared plus b squared. You've also probably seen this as a squared plus b squared equals c squared. Means the same thing, right? And keep in mind, c also always has to be the length of the hypotenuse. It's always got to be the longest side, and a and b are the other two sides. Oftentimes, we have to solve for the hypotenuse, and we can do that by taking the square root of the sum of these squares. In addition, we need to be familiar with sines, cosines, and tangents. These are trig functions that are defined by a relative relationship of the various sides of a right triangle. So in terms of the sine function, it turns out that the sine of an angle is going to be equal to the ratio of the side opposite that angle divided by the hypotenuse. Right, so sine equals opposite over hypotenuse. Keep in mind, anytime you see the term hypotenuse, you know you're dealing with a right triangle. The fact is, hypotenuses are only defined when dealing with right triangles. Cosine, similar, is defined as the function of an angle, which is going to be equal to the adjacent side divided by the hypotenuse. Right? So similar to sine in that it's associated with the angle, but in this case it's the side adjacent to it or next to the angle, and again divided by hypotenuse of a right triangle. The last of these trig functions is tangent. Tangent again is associated with the ratio of sides, and in this case the tangent of an angle is going to be equal to the opposite side, meaning the side opposite the angle, divided by the length of the side adjacent to the angle. So oftentimes it's defined as tangent is going to be equal to opposite divided by adjacent. There are also a lot of mnemonic devices. Mnemonic devices just mean memory devices. For example, you may have heard SOHCAHTOA. Remember, sine is equal to opposite divided by hypotenuse. Cosine is equal to adjacent divided by hypotenuse. TOA, tangent, is equal to opposite divided by adjacent. Another one you may have used is she can tell Oliver had a heap of apples, which is just short for sine, cosine, tangent, and then the various ratios, opposite divided by hypotenuse, adjacent divided by hypotenuse, or opposite divided by adjacent. Whatever technique you use to remember these relationships, it's important to have them somewhere available so you make sure that you have the correct sides associated with the correct functions. So here are these trig functions shown as formula. Fact is, we have sine, which is defined as opposite over hypotenuse, cosine of an angle is defined as adjacent over hypotenuse, and tangent of an angle defined as opposite over adjacent. You can use these in a number of different formats. So for example, if you wanted to solve for the adjacent side, and you knew the hypotenuse, you could say that it's going to be cosine of that angle times hypotenuse. Or if you knew the opposite side, you could say it's the opposite side divided by tangent of that angle. Similarly, if you wanted to solve for the opposite side, you could take sine of the angle times the hypotenuse, or you could take the adjacent side times the tangent. Fact is, all of these sort of interrelate. Similarly, if you want to solve for the hypotenuse, you could say opposite over sine, or adjacent over cosine. All those work well for solving for the various lengths of sides. So how are these formulas used? Well, let's take a look at a simple practical application. Let's say, for example, we wanted to determine how high this building was, and we had no way to directly measure it. Well, it turns out that all buildings cast a shadow based on the sun. The shadow would be on the ground. It would be something that would be pretty easy to measure. And is there a way we could potentially use that to determine the height of the building? Well, let's go through our trig functions and see. The first thing would be to determine the angle of the sun. And the way we could do that is if we had a ruler of known length, say a 1 foot ruler, we could stand that up vertically and it would end up casting a shadow. Based on the height of the ruler and the length of the shadow, we could determine the angle, right? If you think about it, this side over here, the ruler side, is the opposite side, and this shadow is the adjacent side. So using those two lengths and the tangent function, we could solve for the angle of the sun. Right? Once we then have the angle of the sun, we could measure the length of the shadow, and then again we could use that tangent function to determine, in this case, the opposite side based on the adjacent length and this side and this angle. In addition, we need to know how to algebraically manipulate vectors and scalars. To remind you, vectors are any quantity that has both a magnitude and a direction. So for example, your weight is a scalar. You have a certain weight in, say, kilograms or pounds, it's going to be acting downward. An object's velocity is a scalar. It's moving with a certain, say, meters per second in a very specific direction. Scalars, on the other hand, are quantities that are completely defined by only a magnitude. Examples include things like volume. Right? The fact is, a container has a certain volume. It's not acting in any direction. Speed is essentially the scalar version of velocity. When you look at your car, it might be moving at certain miles per hour, but we're not talking about a specific direction at which you're traveling. Now, it turns out that these are going to be used to represent the electrical quantities that we've been discussing, things like voltage, amperage, resistance, power, etc. And we need to be able to add, subtract, multiply these, and divide them. In fact, do any type of algebraic relationships. Turns out most of these can be manipulated relatively freely. There is some limitations. For example, things like a scalar cannot be divided by a vector, etc. We need to take a look at how we go about doing these. Here's a simple example of scalar addition. In this case, we have two batteries, 4 volt, 6 volt. They're aligned in the same direction. So in terms of the scalar algebra, we would just add these two together. 4 volts plus 6 volts equals 10 volts. Similarly, if we had multiple resistors in series, in this case 80 ohm, 50 ohm, 30 ohm, all acting in the same direction, these are also scalars that would add up to a total of 160 ohms. Now, in addition, we can have both positive and negative scalars. In this case here, we have a 4 volt and our 6 volt batteries, but you'll notice the polarity is switched around. So one of them is going to be positive and one of them is going to be negative. Fact is, which one is positive and which one is negative is up to the sign convention that you create. In this case here, we're going to define the 6 volt one as positive and the 4 volt one as negative. When we add these two together, they actually only generate 2 volts, in this case 2 volts in the positive direction. So let's take a look at how we would handle adding multiple vectors together. For example, this is a displacement problem where we're traveling 4 feet at, say, 15 degrees and then traveling 3 feet at 60 degrees. It turns out that the total distance that we traveled would be 7, but what is the displacement? Displacement meaning how far did we move from our original place? It turns out we would need to take these angles into consideration, and the magnitude would be somewhat less, 6.48 at 34 degrees. There's a number of different ways we can do this math. Potentially we could use triangles to solve for it, because of course this is a triangle, or we could use summation of components, using, for example, an x component and a y component to potentially solve this, adding those up. A few different methods available to us. Keep in mind, the idea of triangles works well when you have two vectors, but if you have a whole variety of vectors. Well, this is shown graphically where we have magnitude 6 at 22 degrees, added to a magnitude 3.5 at 135 degrees, magnitude 4 at 56 degrees, and 2.5 at 112 degrees. You could potentially use triangles multiple times, or again, use that idea of summation of components, but you'll find that either one of those will give you a resultant, which in this case is definitely going to be less than the sum of the parts, and the exact angle would also have to be determined. Another important aspect of vectors is if we look at two vectors that originate at the same point, how would we determine the combined effect of these two vectors? Well, to determine this, we can use a technique known as the parallelogram method. This is used whenever we want to add two vectors together. What we can do is we can take one of the vectors and move the tail of this vector to the tip of this vector. Right? And when we combine these two, we can determine what's known as the resultant. The resultant is the combined effect of these two vectors. To summarize all this information, keep in mind we're going to have a variety of AC or alternating current formulas. Many of them are going to be based on right triangles, and keep in mind what makes something a right triangle is that it has a 90-degree or right angle contained within it. One of the relationships we're going to use regularly is the Pythagorean theorem. If you recall, the Pythagorean theorem looks at the three sides of a right triangle, and it turns out that the sum of the square of the sides, in this case of the two smaller sides, is going to be equal to the sum of the square of the hypotenuse. Keep in mind, whenever we look at the three internal angles of a right triangle, they're going to be summing to 180 degrees. In addition, we have a number of relationships between right triangle sides and right triangle angles. The three main ones that we're going to use are sine, cosine, and tangent. If you recall, the sine function essentially expresses the relationship between the opposite side divided by the hypotenuse. In this case, the sine of the angle is equal to the opposite side divided by the hypotenuse. The cosine of an angle is going to be equal to the adjacent side divided by the hypotenuse. And lastly, the tangent of an angle is going to be equal to the opposite side length divided by the adjacent side length. These are all common trig functions that you should be familiar with and be able to do on your calculator. The hypotenuse is only defined for right triangles. It's always going to be the longest side, and it's the side opposite the 90-degree angle. Keep in mind, whenever we look at our trig functions, one is only associated with right triangles. And again, some mnemonic devices like Oscar had a heap of apples or Oliver had a heap of apples. Whichever one sticks in your brain, feel free to use. We also should know the difference between vectors and scalars and the difference between vector algebra and scalar algebra. Vector algebra obviously has to take the direction into consideration. Scalars, on the other hand, can be just added up. And the direction is not important because they're only dependent upon a magnitude. By the way, one other point that's important about both vectors and scalars is you definitely also need units, right? So vectors need magnitude, direction, and units. Scalars need magnitude and units. There's also a great deal of additional information on the course space and in the textbook. And as always, if you have any questions, don't hesitate to get in touch with me.